database. And it is my pleasure to introduce Simon, who will go over ALE and Brainmap.
Thanks a lot. That's supposed to work here? Okay, good. Have to point it this way. So, what is Brainmap? Brainmap has been mentioned a couple of times already. Brainmap is fundamentally a database. So what you've learned over the last couple of talks is that ideally we want to do neuroimaging meta-analysis based on full data, activation maps, or even raw data. And we have some talks after the breaks that cover this topic, but there's one huge problem with it, and that's a huge selection bias. So there are more and more original data sets, more and more statistical maps being shared publicly, but it's only a minute fraction of the entire literature. And it's also biased because that's mainly more recent work. Now people are starting to share original data. That, however, means that anything that's been published the last 20 years would then not go into your meta-analysis. So Brainmap is a tool for coordinate-based meta-analysis, not just a tool, a whole, let's say, ecosystem. And this is working on coordinates. So we can actually go all the way back to the very beginnings of the neuroimaging literature. At its heart, Brainmap is a database which you can enter data into through a particular tool, sluice, Scribe, and we'll briefly talk about that. And up to now, there are about 3,000 papers and about 16,000 different experiments that have already been coded. Remember what Felix said, the difference between a paper and in a particular experiment, and this is critical. I think this is critical for dealing, for organizing and interpreting data. In the same paper, you can have an experiment go trials greater activation than no-go trials, and you can have no-go trials more activation than go trials. It's the same paper, but actually what's neurobiologically behind these two contrasts is the opposite. So if you merge it, you're merging things that are really opposites of each other. Then you can query that database and download data through sluice. Then you can perform your meta-analysis using the ginger tools and share the results through the Anima database. And in the following, I will go and guide you through these individual steps. And I want to do that in a very practical session. So you see mainly screenshots where I point you to, you should click here and you should click there. So one first look at what is in the database. As already mentioned, we distinguish between a paper and an individual experiment, and there's quite a bit of metadata that is associated with each paper. So at the paper level here, what was, for example, the brain template that has been used? Both Jack and Felix alluded to that. That's one of the big problems we have. People use the MNI template. People use the TaylorRuck template. They use MNI convert to TaylorRuck. They use MNI report TaylorRuck but have not converted. They use TaylorRuck and convert to MNI, or maybe they did not, but they still reported it. So spaces and templates are a massive nuisance in the field. Still, in Brainmap, we try to figure out as good as possible what space the coordinates are actually in, although at some point it seems impossible because the paper actually states conflicting information and you cannot find out. So there's this description on the paper level, including all the bibliographic information, and then per experiment we have another set of descriptions. And I won't go into all the details, but what is important here is we obviously have the locations, the X, Y, Z coordinates, where did they report activation, and we have a description of what has been done. So that's basically the paradigm class and the behavioral domain. In a nutshell, this is what you will find in Brainmap. It's papers organized by experiment, and for each experiment you have information on where was the activation and what has been done to yield this activation. As I said, the data can be entered using Scribe, and this is roughly what it looks like. So basically, all the information I just talked about are entered through this interface, and there are actually two versions. There's the full coding, providing all the information, and there's a sparse coding format, which basically allows you to enter data faster, by not providing all of the full information, but really focusing on the key aspects, which is what subjects, whether normal subjects or what is disorder that they have, how many subjects were there, what was the task, what was the contrast. So these things that are critical. I mean, ideally, we want all the experiments coded as detailed as possible, because I think this is where we can really do a lot of the more advanced modeling and, in the end, understanding of brain organization. Still, in order to balance growth and comprehensiveness, I think we are quite good at having the sparse format that allows you to enter the necessary data first and potentially later provide more information. So critical, Brainmap is manually coded, key difference to Neurosynth, and I think in the end there are two different approaches that would be perfectly complementary if you figure out how to put them together. The manual coding can resolve a lot more things, like different experiments, like what was the exact contrast. The automated coding that you have in Neurosynth just grows a lot faster and is a lot better automated, obviously. So there are quite different approaches. What's actually quite good is, in many cases, you see converging lines of evidence from both sides. Not always, and I think that's something we have to figure out later in the hack room. So the labels are manually curated, and there is, as Jack already alluded to, a cross-check, so we really make sure that we are growing somewhat faster, but with very high-quality data in there. These are, as I mentioned, the two critical pieces of information then later. One is the paradigm class that basically describes what has been done, what kind of experiment were the people running. And the second, the behavioral domain, really codes the contrast. So you could have an experiment, let's say on the go, no-go task. Paradigm class would be no go, no-go. And then the activation you get for the go versus no-go trials would then be coded as action execution, whereas the results you get for the no-go versus go trials, you would then see coded as action inhibition. So the combination of paradigm class and behavioral domain quite nicely resolves what has been going on, what's underlying a particular statistical result. Now, as you see here, it's quite a big taxonomy, but it gets a bit more tricky when you get deeply into a particular field. So if you want to get a bird's eye view on the brain, if you want to roughly see what are the where is activity for working memory, where is activity for inhibition, you can do that very well with Brainmap. If you want to do a super detailed coding on all the variants of lexical, reflexive, grammar, third versus first gender in past or present tense, you cannot do that with Brainmap. Then you have to do hand coding, and this recurses back to Felix' talk. The more deep you want to go into a particular field, the more deeply you have to develop your own nomenclature, your own taxonomy. And I can only repeat Felix, really write down everything, because that taxonomy you will revise multiple times. So we now know roughly what's in the database and how it got in there. How do we get something out of it? These are the sluice tools, and this is the basic interface. So what it is a query engine where you can select basically any field in the database I just showed, and then say, well, for example here, the experimental context should be normal mapping. Normal mapping means between contrast. Within group, between contrast. Same people, just two different conditions compared to each other. You then also have disease effects, you have gender effects, age effects, and so on. They're obviously all between subjects. You can ask for the diagnosis being normals. I always found that a bit odd that normal is a diagnosis, but maybe it is actually. And then obviously the number of subjects, how many subjects do you want? Just a different example for a query. Now that goes into something that you can actually set up in about 1 minute. So you say, I want normal mapping. I just want activations, not deactivations, only the high-level contrasts, inhibition, go, no-go trial. That would effectively filter all those studies out of the 16,000 experiments, those experiments out of the 16,000 that basically compared the no-go trials in a go-no-go task to the go trials, right? Because we have the high-level contrast, so it's not against baseline, but against another contrast. Combine that with go-no-go paradigm and inhibition behavioral domain. It basically specifically gets you no-go versus go. Now, let's click on search. And then you first get an overview of what is in the database. That is a bit confusing to first-time users because you don't initially get all the details of the experiments, but you just get that overview. Why is it still good? The thing is, if you want to download all the details from the paper, it does take a little bit. So this initial list of what is there basically shows you already, is it worthwhile continuing with that search, or do I have to refine my criteria? So in this case, there were 70 papers, 190 experiments, so it seems definitely worthwhile to continue with that. And there was just one selected at random, Little 2001, and you see here in green are the matched, in red the non-matched experiments. So it's one paper, and there is the one experiment in that case that was highlighted. So it's just the correct no-go versus go. Remember our search syntax? Obviously, no-go versus baseline was not selected because we asked for high-level contrast. Go versus no-go was not selected because we asked for action inhibition. So this way you can actually quite nicely see what matches your search criteria. Once you're happy with that, you click download, and now you get all the details from the individual papers. Like the full coding scheme plus all the coordinates are then pulled from the database, and you can browse that. You can look, for example, at the citation. What paper is that here? So in this case, mapping motor inhibition. You can look at the subject details over here. So diagnosis normals, 15 subjects, only males. So it's a fairly old paper. At the time, we only cared about male brains, apparently. Handedness was right-handed, and there was quite some age range, which was fairly unusual, actually, at the time. And, for example, here you can look, one field that I like quite a bit, the prose description, basically gives you a short summary of what's been going on here. Again, you can, as you see with these checkboxes, select which of the experiments to actually include or not, and then you go to export locations as a GingerAle text file. And this saves a text file which you can then use to actually perform the meta-analysis using GingerAle. The file looks something like this. Quite trivial. What you have is an order by experiment, and then you have the number of subjects, because as mentioned, this influences the uncertainty estimation, and then you have just all the coordinates. In the GingerAle tool, you open foci, and then this file is loaded into GingerAle, click compute, and it's running the meta-analysis. So, key message I want to bring across here. If you are interested broadly in a map of action inhibition, broadly in a map of theory of mind, the combined work of searching the Brainmap database using sluice and running the meta-analysis is just a couple of minutes. If you want to go more detailed, though, then you can start playing with your inclusion-exclusion criteria. Because remember, we have this rather big search engine there that really lets you go quite specific. Well, I only want to have older subjects, only studies that are at least 20 subjects, only newer studies, only studies, and so on. So you actually do have a lot of options, but still the base time you need is just a few minutes. Looking briefly a little bit more into the statistical part here, because even though Felix and Tom already mentioned it, this talk is not just going to cover Brainmap, but also the ALE approach. What is going on here? Just exemplify that in the working memory experiment again, that has kind of become the standard experiment for showing it. So there are about 200 experiments reporting activation for working memory tasks. And here you see all the activation foci, and you basically see that all your brain has been reported active in working memory studies at some point in time. So the question that we ask here is, where do these foci converge? The key idea behind ALE, as demonstrated by Tom, is that we replace each focus by this Gaussian, modeling the associated spatial uncertainty. So the individual coordinates are not treated as points, but as centers of probability distribution, and the, inverted commas, true location of each reported activation is then modeled by a 3D Gaussian. And the width of that Gaussian is based on an empirical model of spatial uncertainty. Now, if you replace each of the foci by this Gaussian kernel and then summarize across experiments, we get to this kind of probabilistic map that tells you how likely was each individual voxel activated by a working memory experiment. And now we can truly say there isn't a single voxel where the likelihood is exactly 0. So we're not testing against the null model of no convergence. That wouldn't make sense. If you have a big ALE, every voxel would be significant. There's some convergence always. Rather, our null model is the null hypothesis of a random spatial association. So it's not like there's no convergence, but rather spatial location doesn't matter. If we just sample from anywhere in the brain for each experiment and then pool it, it's the same as if we actually respect the spatial pattern. If you do that, you can run the statistical inference and then get areas that are significantly convergent. So these are areas where you have an above chance convergence in working memory studies, and it reflects quite well what we would expect, the sort of broad frontoparietal network. If you're unsure about all what I've said up to now, about ginger ale, about sluice, about Brainmap as a database, if you want to request new features, if you want to report bugs, if you just feel a need to talk, then I'm more than inviting you to look at the Brainmap discussion board, where all of the developers are basically constantly checking what's going on, and we hope to give everybody feedback quite quick and quite satisfactory. Some of the frequently asked questions are those: how many studies do I need? What's the power? And which inference method should I use? Now, this has been talked about already, so I'm going to go very fast about that. We addressed that using ALE simulations. So basically, took the Brainmap database as a fairly good representation of what has been reported in the literature, and then generated random ALE analysis. In fact, 120,000 random meta-analyses where we knew the true convergence, and we knew all the parameters, and ran them. And what we found out is a few things. So first of all, ALE score scales with the number of experiments. The more experiment, the higher on average your ALE score. It's just if you have more things overlap. And then obviously the significance in turn reflects the convergence ratio. So the critical aspect here is, do not report ALE scores. They're completely useless. They don't give anybody any insight. They just scale with the number of experiments. Report statistical values, z-scores or p-values. If we look at the sensitivity to true convergence, we see that for cluster level family-wise error, it's actually fairly sensitive, more sensitive than FDR, and way more sensitive than voxel level FWE. In turn, if we look at false positive or spurious effects, then FDR does a lot worse. So what we concluded from that is that cluster level inference gives you the best both sensitivity and specificity. We can then do also power analysis, and basically it's a little bit shocking. So this is the proportion of the population of studies showing an effect. And basically if you run an ALE with 10 experiments, you only have sufficient power, 80% power, for an effect that is there in half of your experiments. You don't need a meta-analysis. If it's there in half of your experiments, you actually see it by eye. It's quite trivial. If you want to find something that is a little bit more scarce, you're quickly ending up with 20, 30, or even more studies. Underpowered meta-analysis don't help anybody. They don't help you. They don't help the field. And they're still very frequent. So there's still a lot of papers that get submitted with meta-analysis of 4 or 5 experiments. It's just useless. You really have to have sufficient power. It's not like all the basic rules of what you should do in terms of statistics are just out of the window if you go to meta-analysis. Power matters as well here. So what I described up to now is you can enter the data into the Brainmap database using sluice, but you can also use all the data that's already in there, querying it with the sluice function. So here in sluice, you can set up very simple queries in seconds, or you can get as complicated and specific as you want. And I think that's the main advantage. We can have both the quick and easy and the very intricate aspects. You can then analyze the data using ginger ale. And last but not least, I would encourage you to then share the meta-analyses results, share the results you got that represent the convergence of the literature using the Anima database. Thing here is, with the database, we have now a lot of meta-analysis findings that you can then use to look at, but also download it and actually use as a priori information for further studies. So the idea here is that you can use them as priors for primary data analysis. So there is this complex literature on a topic that you are interested in, working memory. Then you do the meta-analysis, or somebody else has done it, and you can now download it through the Anima database. You can use that to represent that particular network of interest, extract, for example, resting state connectomes in that particular network, which gives you a robust representation of that particular function, can submit that, for example, to machine learning algorithms, and then do brain phenotype correlations or prediction analysis in that particular setting. And I think this is something that has a very high ceiling because it combines robust information across thousands of subjects with the predictive power in the individual. Thank you.
Thank you, Simon.